All right, so this is the second part of the lesson on the sine law, or law of sines, what we call the ambiguous case, which means in certain scenarios there can be two possible related but distinctly different triangles that have a lot of the same sort of setup. And for example, if we look at this triangle right here, I want to focus on angle A here and how it relates to the sides around it. So in this case, then the side at the bottom, which again, this arrow represents the length of it may vary. That would be lowercase c. The side over here would be lowercase b, and this is A over here. And then notice I have the height of the triangle shown here, which would, measured from a right angle. So let's say we know angle A, and we know side A, we know side B. Well, there may actually be, if we know all that, there may actually be more than one possibility for how this triangle can look. And so first, let's focus on H for a moment. The height, if we know angle A and we know side B, then the height can be found using right angle trigonometry. For example, if we said the sine of A, angle A must equal H over B, which means the height is always going to be the same as B times the sine of A. Always. Okay, so the height of this triangle can always be found by B times the sine of A. So what matters here is how does A compare to the height? So I'm going to highlight the height here. How does A compare to the height? Well, if A is greater than the height, if the side, and I'm talking about side A here. So if side A is greater than the height, then let's visualize what that would look like here. If side A was longer than the height, that means this side maybe goes like to here or something. Well, then there's the one possible triangle. However, if I keep angle A, side B, and the height all the same, I can actually make a distinctly different triangle if side A is more than the height. And that would be if I imagine this side A kind of rotated over here and imagine it looking like this. And I look at this triangle here. That triangle there has the same angle A, the same height, the same side B, the same side A. But it's a distinctly different triangle. And this is what we call an ambiguous case. We have two different possibilities that have all the same setup. Either the triangle I've kind of shaded in black or the triangle we see in yellow. And anytime we have a setup where, again, we know angle A, we know side B. Anytime that side A is more than the height, there's two possibilities here. So we say there's two solutions. What if A is exactly the same as the height? Well, if A is exactly the same as the height, then this side must be going straight down, which means it's a right triangle, which means there's one solution. There's only one possibility. And what if A is less than the height? If this side A is less than the height, then we have maybe something like you see here, where it just kind of, let's say it stops there. If this length here is less than the height. If that's the case, I don't care where we swing this, we'll never be able to join it up with the bottom, with side C, which means it's not possible. We say there's zero solutions. You can't make a triangle like that. And all of these cases I'm talking about here are implying that A is less than B. Side A is less than side B. And that's what you see in the diagram. That side A is clearly shorter than side B in all these scenarios. What if A was greater than B? If A is greater than B, there's only one possibility. Okay, and I'll kind of show you that here. So if A is greater than B, but everything else kind of set up the same, well, then we have to have something like this. If I keep A right here, let's say, let's say this is B. If side A is greater than B, then this side here has to, if it's longer, it has to look something like this. Again, if I try to swing this over here, it's not possible because it's longer than B. And again, if I try doing that, then this triangle is completely different. And the angle A is just completely changed. So long story short, this sort of scenario is not anything ambiguous. It's really this situation here that really matters. When there are just certain situations, like here, where you can have two distinctly different triangles that have all this other setup the same. And that can really have an effect when you're trying to solve something using the sine law. I'll make one more comment before we actually kind of use this. What if A is an obtuse angle, which means more than 90 degrees, whereas up here, A was an acute angle, something less than 90 degrees. Well, if A is an obtuse angle, and we know, again, everything else, well, then really, there's only one possibility or no possibilities. So if side A is longer than B, there's one way you can do this. There's one solution. And that's if for example, side A is over here, side B is over here. If A is longer than B, and we have an obtuse angle, there's an example of a triangle that fits that. If A is less than B, but we have an obtuse angle right here, it's not possible. Or if A is less than or equal to B, there's no solution. So again, this doesn't really matter too much because it's either possible to make a triangle or not. Again, what really, really matters is this scenario here. And so let's get straight to it. OK, so I want to sketch this triangle or triangles and find the lengths of the missing sides and angles. OK, so I have triangle ABC, where angle A is 39 degrees, side A is 14, and side B is 20. All right, so let's visualize what this must kind of look like, or one possibility. So I'll call angle A right here, 39 degrees, I don't know, something like that. Side B, I'll be consistent and call this side B, just so it kind of relates similar to what we have, which means angle B is over here somewhere. And so I'm not going to worry about drawing something to scale. I'll just draw a line coming down right here. This is side A. Side C is up here. Sorry, angle C is up there. Side C is the bottom. I don't really care about it, though. So with that said, this fits the bill of what we kind of described here. And I know this is 14. I know this is 20. OK, so that said, this triangle I drew may not be the only possible triangle. It may be possible to have a triangle where that side A was drawn right there, which is, again, distinctly different. And so,
well, Mr. Shorey, please contact local 2222. That's Mr. Shorey, local 2222. Thank you.
It's a good thing you heard that. OK, so let's focus. Let's find the height. So if I go the sine of 39 degrees, that'll be the same as height over the hypotenuse of that triangle off to the right, or the left, sorry, which is 20. So h must equal 20 times the sine of 39 degrees. So the height of this triangle I can quickly calculate to be about 12.6 centimeters, or just units. That's my height. So now I know the height is shorter than A. So now I know there's two solutions, two possible triangles. And I didn't really know that for sure until I saw how that side A compared to the height. Which means I'm going to put this on hold, and I'm going to draw the other solution down here somewhere. I'm going to draw the same setup, same angle A of about 39 degrees, same side B right here, that's 20. But this time, actually I just realized I got to adjust this. If I draw side A going this way, I'm just copying what I did before. I know the height, though, is about 12.6. And so if A is 14, I can draw it like right here as well. So actually, let me erase this bottom line. There we go. Angle A, side A, angle C, angle B. And know if I look here, and again, my height is still the same, still 12.6. And the A, again, was 14. But if I compare that triangle to this triangle, they have the same setup, but they are distinctly different. OK, so what really matters is noticing the difference with angle B. I want to find angle B. So let's look at this triangle up here. If I want to find angle B, I can use the sine law. I can say sine of 39 degrees over 14 equals the sine of B over 20. If I solve for B, wrong color. I can use cross multiplying, and we talked about this last lesson, so I'll do this pretty fast. If I want to solve for b, I first go 20 times the sine of 39, divide by 14, and find the inverse sine function of that. And so you can review the last lesson if I did that too quickly, but you should get b to be about 64 degrees. And that looks kind of right. Okay, so that angle there for b looks to be about 64 degrees. Okay, well, let's try to find b in this triangle. Well, if I do the same thing, I'm going to have a bit of a problem, because I can still set it up the exact same way. I can set it up as the sine of 39 degrees over 14 equals the sine of b over 20. Well, it's kind of silly for me to even bother doing those calculations. That's the exact same thing I set up here. But it's clearly a different triangle. So if I do this calculation again, I'm going to get to 64 degrees again. But there's no way that angle there is 64 degrees. And yet I can't just figure it out just by repeating the exact same steps as before, because it's the exact same setup. It's a different triangle, but when I use the sine law, I get the exact same setup. So of course I'm going to get the exact same solution. So how can I figure out that angle b for this other triangle? Well, the key is realizing that 64 degrees is not meaningless. That 64 degrees, again, is that angle right there. Or that means if you kind of swing this side over, that 64 degrees is right there. And so I don't have to do all these calculations again. I just need to realize, again, that 64 degrees is definitely not that obtuse angle of b there, but it's not meaningless. That angle of b must be the same as 180 minus 64, remembering that 180 is half a revolution. Right, from here to here is 180 degrees. And so I don't actually need any of this right here. I can erase all that. That was a complete waste of time. All I need is to go 180 degrees minus the 64 I had from before, and that will tell me angle b. And it's about 116 degrees. I say about because I did actually round 64 degrees up there. And there's my angle b. There's my other option. And that looks right, 116 degrees. So in the end, while there's a fair amount of setup here, once I realized there was two solutions, there wasn't actually a lot of difference in calculations. This triangle here, led me to just really that last calculation of 180 minus 64. And just realizing that that 64 degrees I knew, just from visualizing 64 degrees, had to belong to this triangle up here, not this one down here. There's no way that angle b can be 64 degrees. But it's related to it. All right, so with that said, here is a triangle we actually have. I want to find angle theta. All right, so to find angle theta, let's, it's clearly not a right triangle. Let's just go right to the sine law. All right, so I can say, angle theta is opposite to side 15. Angle 40 degrees is opposite to side 12. So I have everything set up nicely for the sine law. So I can say the sine of theta over 15 equals the sine of 40 degrees over 12. All right, and then solve for theta. And you should get, theta equals, you get the inverse sine of 15 times the sine of 40. All over 12. Right, that's the calculation. And again, that was kind of I spoke about that in the last lesson. So go to your calculator, and theta equals about, because we're rounding, 53 degrees. Okay, that's it. Let's look at my diagram here. There's no way that angle theta is 53 degrees. This is an acute angle, less than 9 degrees. This is an obtuse angle, more than. So either we made a mistake with our calculations, or we have to kind of build upon what we were just talking about in this lesson, really. So I didn't make a mistake with the calculations. So 53 degrees is not that angle. But again, 53 degrees does mean something. 53 degrees would be correct if the triangle looked like this. If this side of 12 meters was drawn this way, and everything else was the same. Still at a 40-degree angle right here, still at a 15-meter measurement right there. Everything else is the same. I've just kind of imagined swinging that 12-meter side over here. And that then would explain what this 53 degrees is. That's right there. That looks right, which means this is also 53 degrees. And so again, like before, angle theta is not 53 degrees, but I can figure it out by going 180, take away 53. And that's, again, the idea. So in the end, once I realize this is not so much incorrect, it's just not the angle I want, know the theta we want is going to be, again, 180 minus 53 degrees, which is 127 degrees. Whoa, helps if I can write numbers properly. That looks correct. And so again, still quite quick. The trickiest part is realizing, it really just, for example, for this question, if we just took not even 10 seconds, 5 seconds to pause at this point and just look at our answer and then compare it to our diagram, we know something's wrong. We know that can't be 53 degrees. One of the most common mistakes is just not pausing to think about that and just getting an answer and moving on. But with that said, we're all good.